Hello, welcome back to our NPTEL course on scanning electron, ion and probe microscopy in material characterization. In last few lecture, we have discussed on scanning tunneling microscope, which is a type of scanning probe microscopy. So, under that technique, we have discussed how 3D image can be achieved using the tunneling current. Today, we will begin with another probe microscopy, which is called atomic force microscopy. Now, there are two new words coming with this microscopic technique. One is atomic and middle one is force microscopy we have already discussed. Now, the atomic means something related to atoms, which is nothing but here the force between the atoms. We will see here also we use a probe, physical probe, to measure the force, and using that force when we create image, then it would be called as atomic force microscopic image. And this is alternatively called as scanning force microscopy, because here again the physical probe is used to scan over the surface. So, it will be scan across the surface, that is why it can be also called scanning force microscopy. And we will see, before we begin with atomic force microscopy, what are the disadvantages or limitation of scanning tunneling microscopy. But before that, as you see in the slides, we have a lot of techniques under the umbrella of scanning probe microscopic technique. In one case, we say scanning tunneling microscopy. Here, rest of the microscopic technique has mostly force word is incorporated. So, in all other categories, we measure a certain type of force and utilize that force to create the surface image. That is why we say corresponding force microscopy. And as of now, scanning tunneling microscopy is used exclusively to study the very surface of a material with atomic level resolution, and it is mostly done under a ultra high vacuum, though it can be also carried out under liquid or in any environment, and it gives a very high resolution scanning tunneling microscope by measuring the tunneling current in the picoampere nanoampere level. But all other techniques, let us say atomic force, magnetic force, chemical force, are more widely used, and almost in all research laboratory and even in the universities, this atomic force microscope is used in these days to study the film roughness, particularly thickness of the film and other type of information. So, we will begin today with atomic force microscopic technique. Before begin, as I say, let us talk about the limitation of scanning tunneling microscope. Scanning tunneling microscope is used to measure or study the conductive sample only, the sample which is conducting. That means a sample should be either metals or semiconductor, because here we measure the tunneling current. So, without the sample being conducting, we cannot measure, we cannot get the current out of the sample. In particularly, this is the tunneling current, and we use atomically sharp tip, because we get information at the atomic scale. So, the tip should have a single atom, then only we can get information or current passing between two atoms, one atom in the sample and one atom in the tip. If our tip is dull or tip is blunt or tip has a larger size, then our lateral resolution also will degrade, or the image can have artifacts. So, the dull probe or multiple tips would become a problem for scanning tunneling microscope. Moreover, as we measure the tunneling current, and tunneling current can only be measured when the tip and sample can brought very close to each other at a distance of few angstrom, and therefore, we should have a complete vibration isolation. Any type of small vibration cannot be acceptable to get information at the atomic level. So, one of the issue is the subject to noise. Moreover, it has quite complex and expensive instrumentation, though practically it can be shown, but in order to really study the surface of a material, the surface has to be ultra clean, then only we can see the atoms of the real sample or the sample to be examined. If we take any sample to study under the microscope in any environment, then sample will be automatically the sample surface will be contaminated in the environments, and therefore forming different type of layers, few layers on the surface. Then actually we will be examining those contaminants on the surface rather than the real sample. So, most commonly STM is studied under ultra high vacuum system or chamber. So, one of the major limitation, as you see in this scanning tunneling microscope, is that it is only suitable for metal and semiconductor sample, but it cannot study the insulating sample. So, in order to avoid that demerits or disadvantages limitation, atomic force microscope come to rescue, and in the atomic force microscope it works by scanning a physical probe over the sample and building the map of height or a 3D profile of the surface, and it is done by taking a tip with a radius of around 5 to 10 nanometer. Unlike in the previous STM cases, the tip has to be a single atom. Here tip can be little bigger, and when the tip will touch the surface and records the force between the tip and sample. So, the force is measured between few atoms at the tip and few atoms at the surface, and that force is utilized to create the image. Like if we have two different materials on the surface, the force between tip between one materials with tip and other materials with tip will not be same. Similarly, if the sample has roughness, then when the tip is going above the sample, tip is scanned above the sample, the force at different location will no more be same, the force will be different. So, by measuring the force, different force at different location, we can construct an image where there is a small gap between the sample and tip, and where there is a large gap between the sample and tip. In this way, by measuring the force, we can create a 3-dimensional image of the sample using the atomic force microscope. It was discovered certainly after invention of the scanning tunneling microscopy. Scanning tunneling microscope was discovered in 1981, and then in 1982 they could demonstrate or show the arrangements of the silicon atoms, one plane silicon atoms very clearly, atomic arrangements. And as we discussed, one of the demerits was not able to study the insulating sample. Then just 5 years after, 4 to 5 years after, there are 3 scientists, Binning, Quat and Gerber, demonstrated another type of microscopy, which is a type of modified scanning tunneling microscopy, to measure the surface topology of the sample by measuring the force. So, they used again scanning tunneling microscope to measure the force as small as 10 to the power minus 18. So, they could measure a force as small as 10 to the minus 18 Newton, and with this microscope they could study the surface of the insulator on an atomic scale, and here they could achieve, the first microscope could achieve a lateral resolution of approximately 3 nanometer and a vertical resolution less than 1 angstrom. So, with a modified version of scanning tunneling microscope, they could achieve a vertical resolution less than 1 angstrom, and because they measure the forces between the tip and sample, and with that force they create the surface topology, they term it force microscope or atomic force microscope. So, in this newly developed microscope, they used a STM, and where they used a cantilever beam with a very small mass, and using that cantilever they measured the force between the tip and sample, and they, that cantilever beam can displace a distance of 10 to the minus 4 angstrom by applying a force or by measuring a force of around 10 to the minus 18 Newton. So, this new microscope was constructed by gluing a tinish shard of diamond onto an end of the gold foil. Here gold foil acts as a cantilever, and here tip is made up of diamond. As you know, in scanning tunneling microscope, the tip is made up of a tungsten or platinum iridium. Those are metals, because we need to measure the tunneling current between the tip and sample. Sample has to be conducting or semiconducting, and tip has to be metallic. In this case, as you see, the tip is no more conducting, neither metal or not semiconductor. It is a diamond which is insulating. So, using a diamond tip, they scanned the surface and tracked the deflection of the cantilever by monitoring the tunneling current using a second tip above the cantilever, diamond and cantilever assembly, and using that they have successfully examined insulating surface or created the surface topology of insulating material. So, as you see the design of the first microscope. So, here in this design they have taken a sample, AFM sample here, and AFM sample is placed on a scanner and AFM feedback, atomic force microscopy feedback. Scanner is for moving the sample in x y direction, and feedback is to control the movements in the z direction and other direction also. Then we have a, here we have a cantilever, as you see cantilever here, cantilever is made in gold above the sample, and the at the one end of the cantilever there is a diamond tip, AFM diamond tip, and above the cantilever there is a simple STM system. This part is STM system, STM tip and STM feedback. Now, because STM measures the tunneling current, therefore, cantilever is made in gold, but on the gold at the one end of the at the tip at the one side of the cantilever, the diamond tip is fixed. Then we have a modulating piezo here to control the moments of the cantilever in the z x y z direction, and it is placed on a aluminum block. So, they have measured in different modes, there are 4 different modes they have shown demonstrated. In the first 1 to 3 mode, they kept the constant force between the sample and diamond tip. So, the sample was modulated in the z direction at its resonant frequency, which in turn deflect the cantilever and dodge the tunneling current. So, for example, our sample is like this, our diamond tip with cantilever is moving above the sample, then in order to measure the constant force between the tip and sample, the cantilever has to bend upward or downward, because the constant force will only occur when there is a similar distance or same distance between the sample and tip. Constant force will only occur when there is same distance between the tip and sample, and when therefore cantilever has to bend downwards or upward, and when the cantilever bends, the distance between the STM tip above the cantilever, distance between the tip above the cantilever will be either far away or close to the cantilever. And as the gap between the STM tip and cantilever changes, tunneling current changes. So, that tunneling current was utilized to create the images, as when the tip will come down to measure constant force, and in order to measure the constant force, tip has to come down when the sample position is towards downward, and then at that places tunneling current will decrease. So, using that tunneling current, one can construct an image. And similar way, other modes also work in second, third mode, where the cantilever is driven in z direction at a particular resonant frequency, and then their amplitude and phase changes was monitored by modulating the tunneling current, which can be used for imaging purpose. In this way, it can also be possible to create the image. In the fourth mode, it was not the constant force mode. Here one feedback circuit was used and it was controlled by the tunneling current, and this was maintained by tunneling the gap by changing the force on the cantilever. So, by changing the force on the cantilever, so force changes as the gap in order to maintain that same tunneling gap, in order to maintain the same tunneling tunneling current, the force can changes, and that force can be used to create a 3-dimensional image. In this way also one can create 3D image of the sample. So, how force is measured? So, as you see here, we measure the force, and it can be and we use cantilever, and the probe and tip is fixed at one end of the cantilever, and the amount of the force between the probe and sample is dependent on the spring constant of the cantilever and its deflection. We know simple Hooke's law. Hooke's law F is equal to kx, or here it is minus, because we have taken an example of spring, and the spring is attached to a support, and at the bottom let us say we have a pendulum, and the spring will stretch, and this stretching or displacement depends on the how much force is put on the spring, or how much weight of this pendulum. Accordingly, that much of force can be placed downward, or displacement will occur. As the restoring force in these cases is in the opposite direction, therefore, it is in minus here, taking the example of spring. So, here force is directly proportional to the displacement. So, F is the force, and here K is important in the spring constant and cantilever deflection. If the spring constant of the cantilever is normally in the range of 0.001 to 10 Newton per meter, if the spring constants of the cantilever is less than the surface, cantilever will bend. And deflection will occur, and we can measure that deflection to know how much cantilever is bending, and then accordingly we can create a 3D image, as you will see later more in a more detailed manner. So, there are different forces. The total force between the sample is composed of several long range and short range forces. Like short range forces includes like chemical bond, different type of bond, and the short range force are when the tip and sample are less than 0.5 nanometer, when the distance between the tip and sample is less than 0.5 nanometer, there will be a short range forces such as chemical bonding etc. And we can have also long range force like van der Waals forces, and long range forces include capillary, electrostatic and magnetic force, and these type of force can also be measured using the atomic force microscopy to study the respective properties. For example, in one sample, in one cases in the sample there are few region we have a magnetic samples are there, magnetic particles are there, in other region no magnetic particles are there. Then when if our tip go or probe go above the sample, then it will detect, and certainly a tip has to be also magnetic in nature, then only the magnetic force can be measured between the tip and sample. If the tip has a certain magnet and your unknown material has some magnetic particles in it, then when the tip scan over the surface, then it will see a different type of force, that is a magnetic force in the region where magnetic particles are present. And here tip has not to be tip has not to come very close to the sample, because magnetic force is a long range force. It can even the tip is more than 2-3 nanometer or 5 nanometer, 10 nanometer away from the sample surface, still tip can experience the magnetic force, and by measuring the magnetic force we can know wherever the tip see a magnetic force, we know that magnetic particle is present in that region. So, we can tip can scan from one side to other side, left to right, and produce a force map, magnetic force map, and thus creating a magnetic force microscopic image, telling us how the magnetic particles are distributed on the sample. Similarly, all other type of forces can be measured, electrostatic force, capillary force, frictional force, all kind of forces can be measured using this technique. We will not cover all those forces, but some of those techniques we will cover in this course. So, if we look at the capabilities of atomic force microscope, it can give us or provides us different material properties, including the electrical properties. Electrical properties are normally measured by Kelvin force microscope, electrostatic force microscope, conducting AFM. Here we say conducting AFM. In case of conducting AFM, the tip has to be conducting in nature, though theoretically we do not need a conducting tip, as we have seen in the first invention they have used diamond tip. But if we want to study the electrical properties of a sample, or let us say on any insulating substrates, we have a conducting wires placed in a particular manner, then also or a type of this kind of conducting layers is present in the sample with a particular distribution or arrangements, then we can use a conducting tip and measure the current passing at different region across the sample and get an information where this conducting layer presents on the sample. Piezo force, similarly piezo force can be measured. Optical properties can also be measured like near field Raman and near field IR. Mechanical properties such as lateral force, shear force, torsional resonance, force modulation, contact resistance, all these kind of properties can be measured with atomic force microscope. We have already discussed magnetic properties in a brief way. Other capabilities of this probe microscopy is surface manipulation and lithography. As here we use a physical probe. Using this physical probe, I can put this physical probe into an ink, let us say, and bring this probe to write anything I want on a surface. So, thus I can write on a surface using my tip. If my tip is in atomic, I can write in atomic scale, or if there is something on the surface, let us say a nanowires is there on the surface, I can use or take that tip to displace the tip to a different position, or I can bend the nanowires, let us say carbon nanotube with straight carbon nanotube using this probe. One can bend that carbon nanotube to the desired position or desired angle. So, this is nothing but surface manipulation or manipulation of the nanomaterials. All these kind of things can be done by atomic force microscope. Primary application of the atomic force microscope, we see mostly the students on the research laboratory or in the academic laboratory, what is being done to measure the surface topology, 3D features of the surface. Surface roughness analysis, it is most commonly used by this technique when we want to measure the RMS roughness or root mean square roughness in a small area. So, accurate surface roughness can be detected to a level of sub angstrom levels, the height or roughness range in a sub angstrom level, less than 1 angstrom, one can measure surface roughness. Step height measurements with high accuracy. Step height means in the lithography and in device making there are different steps. We can measure what is the height of each steps in the angstrom range. Certainly, we can measure the thickness of monolayer or 2D materials or like graphene, nanosheets, all kind of these kind of 2D materials thickness is most commonly measured by atomic force microscope, like the same way the step height is measured. Pinhole formation analysis in oxide. So, if there is pinholes in a surface, we can accurately measure the height of the hole or depth of the hole, which cannot be measured by other techniques such as scanning electron microscope or helium ion microscope. Quantitatively, we cannot measure the depth or vertical height, but it can atomic force microscope and scanning tunneling microscope can be used for this purpose. Using the phase imaging mode, we can also get information about surface stiffness, elasticity, adhesion, frictional force, all these kind of study, like sample may be flat in some region if there is a different type of material is present in these cases, then its adhesion or other type of properties may be different to here. This region is different and this region is different. So, even though the surface is at the same height, but actually as the materials are different, they will have different characteristic. So, those things can be measured by atomic force microscope. So, these are the main application of atomic force microscope, and in conclusion what we see in this introduction that atomic force microscope finds wide applicability among the family of scanning probe microscopic technique to examine wide range of sample in any environment, as here again physical probe scan over the surface. Therefore, we do not need vacuum, we can use under air, we can use it under liquid like the scanning tunneling microscope, and it measures the force between the tip probe and the sample surface as a signal to construct the surface topology. And as different forces exist on the sample surface, we can use the forces for measuring respective property of the sample, and AFM is achieved AFM has been used to achieve a lateral resolution less than 1 nanometer and vertical resolution less than 0.01 nanometer, very high super resolution vertical resolution. There is no other technique can provide such kind of high resolution vertical resolution. And for the AFM measurements, we do not require conducting sample. all kind of samples can be done, one of the major advantage of atomic force microscope. References are here, and thank you.